Okay, in the last class, we were talking about the discrete random variable. And we talked about some of the very useful properties of a discrete random variable. And we said those useful properties of discrete random variable are, number one, the probability distribution or the probability mass function, which is basically two columns. One of the columns is the values of X. And the second column is the corresponding probabilities. And we said that the sum of this column will always be equal to 1. And we said that these probabilities are basically the functions of X. We later discovered that we can also write it as a probability mass function, where every probability was nothing but the function of X. Here in the yellow color, I wrote that probability mass function as a function of X. And this function of X is denoted by small f of X. In the literature, if you see, this function of X is denoted by small f of X. So we said these two columns, collectively, these two columns are called probability distribution or probability mass function equivalently. Now from this table, if you are interested in probability of X at a specific point, you can just go to that row and pick the value. For example, if I'm interested in probability of X equals, let us say 7, I'll directly go to the row where X is 7 and pick the value. My answer will be f of x7 directly. That's the first use of that table. Now the second use of this table is, what if I'm interested in probability of X less than equal to 7? Less than equal to 7 mean all the probabilities will be added up to 7. So that will be probability of x1 plus x2. That will be f of x1 plus f of x2 all the way up to f of x7. What if I'm interested in probability of X less than equal to 13? That will be on the similar lines, f of x1 plus f of x2 all the way up to f of x13. And this is very common question where we ask you to find less than or equal to probabilities. So whenever we ask you to find equal to, less than or equal to probabilities, every time you will start adding from the lowest value of X all the probabilities up to wherever it is required. So it's time taking, you add all these probabilities every time. Instead, we define a function right at the start, like we defined small f of X. We also define a capital F of X. And this is basically the probability of X less than equal to X. In this capital F of X, we actually add all of them up to that specific point. So the probability, this capital F of X1, this will be probability of X less than equal to X1. And that will be simply probability of X1, which is F of X1. For the first one, it will be simply F of X1. Added up to the first one. For the second one, it will be capital F of X2. This is going to be probability of X less than equal to X2. And this will be F of X1 plus F of X2. For the third one, it will be capital F of X3. That is probability of X less than equal to X3. And this is going to be F of X1 plus F of X2 plus F of X3. All the way up to the last one will be F of Xn. This is going to be probability of X less than equal to Xn. And this is going to be equal to F of X1 plus F of X2 plus all the way up to F of Xn. And who can guess what will be the final answer of this capital F of Xn?
It will be 1.
It will be 1. The last value of this capital F will be 1. Because you are adding all the probabilities. And the sum of all probabilities is always 1, as we said in small f of x. So that is the difference between small f of x and capital F of x. At any point, if you are interested in equal to probability, you will be using small f of x. And if you are interested in less than or equal to probability, you will be using capital F of x. So this can be written as capital F of X7. This can be written as capital F of X13. That's the second major use of this probability distribution. The third major use we discussed was to find the mean of the variable, which is either denoted by expected value of X or mu of X. And we said this is basically what summation X times F of X. I'll call it F of X. So you need this new column where you multiply X and F of X, and then the sum of that column is mean. The fourth use we talked about was the variance of X, denoted by sigma square of X. And this is summation X square times F of X minus mu of X square. So you already have mu of X from third use. You create another column like X squared times F of X, and the sum of that column will be this part. And then you subtract the square of mean. That will be your variance. Similarly, the standard deviation, that will be sigma of X. This is going to be the positive square root of sigma square of X. Now this is true. These 4 points that I just wrote, these 4 points are true for every discrete random variable. Last time we did an example of a discrete random variable where we were picking with replacement. Let us do an example here where we pick without replacement. So assume you have a box of 10 items. 7 of them are working. 3 of them are defective. And suppose you pick 4 of them. Without replacement, without order. And you denote X by number of defectives. Not working, defective. Now we'll go step by step. What is the first step? The first step is what are the possible values of X? Raise your hand if you know what are the possible values of X. X is the number of defectives. I picked 4. Jafar. Jafar Muhammad.
3/10.
Possible values of X. Number of defectives. Can it be 0? Can I have 0 defective in my sample of 4?
Yes, I can have 0.
I can have 0. Can I have 1?
Yes, I can have 1.
Okay. What else?
2.
2 is another possible value.
And 3.
And 3. And I'm picking 4. Can I have 4?
No.
Why?
Because I only have 3 defective objects.
Yes, we have only 3 defective in the population, so I cannot have 4 defective in my sample. So these are all the possible values of X. The second step, as we said, is to find small f of X, which is probabilities. This we are going to call small f of X. So the probability of X equals 0. Who can tell me the expression? Raise your hand. Probability of X equals 0. I pick 4 and I get 0 defective. That means all 4 of them are working. Nawaf Ali. Nawaf, I cannot hear you. Yes. I cannot hear you, Nawaf. Abdul Aziz. Abdul Aziz, we cannot hear you. Muhammad Ali.
I calculated the probability and it is equal 0.1667.
0.1.
667.
667. And what is the expression? Can you tell us what is the expression? How did you calculate this?
7C4 multiplied by
7C4 multiplied by
3C0
divided by
10C4.
10C4. I saw another hand raised. Raise the hand again. Who was that? Ali, tell me what is the probability of X equals 1?
It's 7C3 times 3C1 over 10C4.
Right. And similarly, Paris, what is the probability of X equals 2?
C72
C72
multiplied by 372. 3C2, sorry.
3C2.
Yes, and divide by 10C4.
10C4. Ali, what is probability X equals 3?
Sorry, Doctor. C7C1, I think.
7C1?
Yes. The last one.
The last one.
Right?
7C1, absolutely right. So we have 7 combination. Or multiplied by 3 combination 0 all divided by 10 combination 4. That is 1.1667. Then I have the second one equals 0.5. The third one is 0.3. And the last one is 0.0333. And even without calculating, I should have this one, the sum equals 1. This column is my probability distribution, probability mass function. That's the first use. The second use is what if I'm interested in capital F of x. That is, I'm interested in probability of x less than equal to x. So that means the probability of x less than equal to 0. That will be simply 0.1667. Probability of x less than equal to 1. That will be 0.5 plus 0.6667. So that will be 0.6667. Probability of x less than equal to 2. That will be 0.8667. And probability of x less than equal to 3 will be definitely 1. So this column is called cumulative distribution function, capital F of x. I forgot to write the name of this thing. This is called cumulative distribution function, abbreviated as CDF. Muhammad Faris.
Yes, Doctor. Could you go down, please?
Go down. Okay, here.
Yes, I think probability of x less than or equal to, it is 0.9, not 8.
0.9, yes.
Yeah.
0.9667. Nawaf. Okay.
Yeah, I just had the same
Same comment.
observation.
Yeah, I got it. So these are the two uses. Now, if this table is given to you in the question and I ask you what is the probability that I pick 4 and I get at least 2 defective items, what should be your answer?
Sorry, could you repeat your question?
I pick 4 items without replacement from these 10 items. What is the probability that I get at least 2 defective items? Jafar.
0.3.
0.3. I said at least 2. Okay, let me ask the simple question first, and then I will ask at least 2. What is the probability that I will get less than equal to 2? Ali.
It is 0.9667.
Less than or equal to 2 defectives. That's directly 0.9667. You don't need to calculate. You don't need to calculate again. This is coming directly from the table. Now, what if I ask you the question that find the probability that I get at least 2 defective? What will be the answer? Those who know the answer, keep the hands raised. Those who don't know, unraise your hands. Ali Al Hassan, at least 2.
Same answer.
You said same answer. 9667. Okay, this is one opinion. Ahmad Raid.
Same answer.
Same answer. Okay, Yusuf Zaid.
I think it's 0.3333.
It's 0.3333. Can anyone tell me what does at least mean? In terms of expression, Hussam Ali. At least 2. What does this mean?
Greater than or equal.
Greater than or equal to 2. Now who can tell me the answer? Amjad Ammar.
0.3333.
0.3333. And where does this come, Amjad Ammar?
0.3 plus the 0.0333.
Yes, it's not the last value in the table of small f of x. It's the sum of the last 2 values.
Doctor.
Yes.
I can use the complement of x less than 2, right?
This is 1 minus capital F of 1. Yes. What is the expected number of defective items? What am I asking in the question?
The average.
The average. I'm asking for expected value of x or mu of x. So for this, I need 2 more columns. I need x multiplied by f of x. And for the next question where I'm going to ask for variance or standard deviation, I need x squared times f of x. So I'll create these 2 columns together. So this is going to be 0 times 0.1667. This is going to give me 0. And this is 0 squared times 0.1667. This is also going to give me 0. This is going to be 1 times 0.5. This is equal to 0.5. And this is also equal to 0.5. This is 2 times 0.3, which is 0.6. And this is 2 squared times 0.3. This is equal to 1.2. This is 3 times 0.033333. This is going to give me 0.0999. And this is 3 squared times 0.330333. This is going to give me 0.2997. If I round up to 4 decimal points. And the sum of this one is 1.1999. And the sum of this one is 1.9997. So from these two columns, I can simply find my mean equals 1.1999 and my variance equals 1.9997 minus 1.1999 square, and this is going to be equal to 0.5599. Accordingly, the standard deviation will be 0.5599 square root, which is 0.7483. So these are all the uses of probability distribution that we may ask you in the question. Another small question. What if I ask you probability of x between 1 and 3, including 1 but excluding 3? Omar Adnan.
Probability of x equal 1 plus probability of x equal 2.
F of 1 and f of 2. Small f of 1 and f of 2. That will be 0.8. So accordingly, you can answer any type of question from probability if you have this table. And we can ask you the question both ways. We can ask you to create this table also, and we can give you this table and ask questions out of this table also. Any question from probability distribution? Okay, this was all the concept of probability distribution of a discrete random variable. These are general concepts which are applied to any discrete random variable. You can apply these concepts on any discrete random variable. Now we are going to go specific. There are some special distributions which are so commonly used that they are given special names in practice. Now the concepts I just discussed in the first 30 minutes of the class, these concepts are also applied on these special distributions. But because these special distributions are so commonly used in application that we give special names for them, and we have the shortcut formulas for the mean and standard deviation for them. That does not mean that these general formulas of finding mean and variance does not apply to them. They do apply to them. But the shortcut formulas also apply to them. The first of those special distributions is called discrete uniform distribution. A random variable is said to have following a discrete uniform distribution if its probability mass function can be written as 1 over xn minus x1. Where x is starting from x1 and then x1 plus 1 and then x1 plus 2 and all the way up to xn. The mean of such variable, which is denoted by mu of x, is simply x1 plus xn over 2. You don't have to go to the basic formula summation x times p of x. Even if you go to that one, you'll get the same answer, but this is a shortcut formula. The variance of such random variable, which is denoted by sigma square of x, that is equal to xn minus x1 plus 1 whole square minus 1 over 12. Again, you can find the variance by this formula also. Where is it? This formula, but it will take more time. Here, this is a shortcut, and this shortcut is only applicable on a discrete uniform random variable. This is not a general formula. This is specifically for discrete uniform. Now, by the look of the variable, you should be very clear that what type of variable has a discrete uniform distribution. A variable that has like 10, 12, 13, 15 values, and all of them, they have the same probability. 1 over xn minus x1. Let me give you an example of a discrete uniform random variable. Let me go to your book. And pick a question. This is section 3.5, by the way. And the question says, this is example 3.14. I'm going to copy this example. It's on page 101. So here is the example. It says, let the random variable x denote the number of 48 voiced lines that are used at a particular time. Assume x has a discrete uniform distribution with a range from 0 to 48. So this 0 is basically the smallest value, and this 48 is basically the largest value. x1 is 0, xn is 48. That's the first thing you need to identify whenever you see this word in the question, discrete uniform random variable. Whenever there is a discrete random uniform random variable, you need to identify what is x1, what is xn, the smallest value of x and the largest value of x. Everything depends upon x1 and xn. Jafar Muhammad.
Doctor, this statement will be always written in the questions.
Discrete uniform random variable, if there is a question about discrete uniform, it will tell you about discrete. It will give you the word discrete uniform random variable.
Okay, thank you.
So if you want to write the whole probability density function, which I don't recommend you to write, if you want to write the whole probability density function in terms of table, you can write that. Again, I don't recommend that. That will be like this: 0, 1, 2, all the way up to 48. And every value has an equal probability. That is 1 over xn minus x1, 48 minus 0. This is 1 over 48, 1 over 48, 1 over 48, and all the way up to 1 over 48. Every value has an equal probability. What I recommend is you should write this as a function, and that function will be probability of x equals x. This is also denoted by f of x. This should be 1 over 48 minus 0, where x is from 0, 1, 2, all the way up to 48. This is how I recommend you to write the probability mass function in terms of a function, not in terms of a table. In general case, I prefer to write it as a table because sometimes it can be converted to a function, sometimes it cannot be converted to a function. So table is okay. But once I go specific, special, like uniform, then the functions are available in literature, so it's better to write it as a function. Nawaf Al-Shahri.
Excuse me, Doctor, but I don't understand how they can all have same probability.
There are 48, 49, sorry, there are 48 values or 49 values?
48.
One over, sorry, this is 1 over n. The number of values. There are 49 values basically, including 0. Including 0, there are 49 values. And the sum will always be 1. Yes. Is this what you were indicating or something else?
No, I meant like how if we had like number x equal 3, how can the probability be the same as if x were 2?
This happens in applications where you are, cutting something with respect to the length. So what is the probability that the final length will be, let us say, 1 millimeter? The probability is something. What is the probability that the final length will be 2 millimeters? It's the same probability. So the cutting tool, if it is cutting randomly, so the probability that the tool will cut from anywhere, they have the equal probability. It can press at 1, press at 2, press at t. So any point the cutting tool can press it.
Okay, I see now.
Yasir Ali.
Yes, Doctor. So we consider if x is a probability of 3 is the same probability of 2 because he mentioned in the question uniform, right?
Yes, all the probabilities are equal.
Okay.
Muhammad Faris.
Doctor, I have a question for the mu equation. This average, can I use for the previous question?
No, this is specifically for discrete uniform.
Only for uniform, okay.
Yes. And we will discuss more special distributions. This is the first one. All of them, they have their own mean expressions.
Okay.
So we cannot use the mean expression of one special distribution in another one. So what if I ask you to give me the mean of x? So the mean of x, there is one way you go the definition. That is, you multiply x with f of x, then you take the sum of that column. That will give you the same answer. The one I'm going to use the shortcut here, which is x1 plus xn over 2. So that will be 0 plus 48 over 2. The mean is 24. Even if you go that way, you'll get the same answer.
Yes.
The standard deviation, sigma of x. Again, you can go the definition, the general case, but I'm going to use the shortcut case here. It is the square root of xn, which is 48, minus x1, which is 0, plus 1, whole square, minus 1, divided by 12. And this is going to give me 48 plus 1 is 49. 49 square is equal 49 square plus minus 1 divided by 12 minus 1 divided by 12, and then the square root of this whole thing is 14.142, and this is 200 square root, and this is 14.14214. This is the standard deviation. Again, you can use the definition here also. This definition, where is it? This one also. But that will take longer. Muhannad Shafiq.
Doctor, is this formulas is the same for the lab, or they are different?
Which formula for the lab? Now, this is the question I left you at the end of the last class to think. And thank you for reminding me and taking me back. There is one formula in the lab for mean. There is one formula here in the class for mean. In the lab, you said the mean is denoted by x bar, and you said this is summation x over n. Or if there are frequencies, you said this is summation fx over summation f. And in here in the class, you said there is mean. It is denoted by expected value of x or mu of x. And this is summation x times f of x. And these two are different things. And what is the difference? Both of them are called mean. And I left you with this question. What is the difference? And I'll still not tell you the answer. Remind me in the next class again if you don't get the answer. This is lab. This is class. And same is true for the variance. There is a formula of variance in the lab. There is a formula of variance in here. And we're looking for the difference between these two. Any other question? Muhannad, remind me in the next class if you don't find the answer of this one. I'll give you the answer.
Okay.
Any other question from discrete uniform random variable? Okay, let me ask you a quick question. X can take the values 0.1, 0.2, 0.3, 0.4, all the way up to 1.9. These are all the possible values of X. Is this a discrete or a continuous variable? Raise your hands if you know the answer. Muhannad Shafiq.
It's not, it's discrete.
Muhannad Shafiq said it is discrete. This is one opinion. And what is the reason, Muhannad?
Because it's jump, not 0.1, 0.11, 0.112. We jumped.
Okay. Muhammad Faris, what is your opinion?
Same thing. It is
same
discrete.
thing. Jafar.
I agree with them.
Ali Abdul Rauf.
Same thing, because we
Same
have
thing.
only
Yes,
specific
this is a
values.
discrete. Same thing. But what if I write that x belongs to a domain 0.1 to 1.9? Muhannad. Nawaf.
This is no longer discrete.
This is no longer discrete. This is continuous now. So if I tell you the domain of x like this one, you cannot apply this thing here. The distribution we just discussed is discrete uniform distribution. Keep in mind, when we go to chapter 4, there will be another uniform distribution that will be a continuous uniform distribution. Do not confuse this one with that one. That is continuous uniform. This is discrete uniform. Two different distributions. Okay, let us move on to the second special distribution. The first special distribution was from discrete chapter. The first special distribution was discrete uniform distribution. The second special distribution is called binomial distribution. And this is the toughest section of this chapter. If you understand this section, you will understand the remaining 3 sections also. If you don't understand this section, you will struggle to understand the remaining 3 sections. And this is the distribution where most probably in question, it will not use the word binomial distribution. You have to identify that x is binomial from the properties of binomial distribution. And I'm going to tell you those 4 properties. For every binomial random variable, those 4 properties are satisfied. And those 4 properties are, number 1, the random variable is coming from a random experiment which has only 2 possible outcomes. There will be only 2 possible outcomes. The way we were doing this question, the defective and working. So in this experiment, there will be only 2 possible outcomes. You will be interested in one of them. Sometimes you are interested in number of working. Sometimes you are interested in number of defectives. So we call the one where we are interested, we call that one as success and the other one as failure. Just the notations, no special meaning of this success or failure. Wherever we are interested, if you are interested in number of working objects, you will call working as success and defective will be failure. If you're interested in number of defectives, then defective will become success and working will become failure. So no special meaning, just the notations of success and failure. If you have such experiment which has only 2 possible outcomes, success or failure, number 2, probability of success remains fixed. Number 3, trials are independent. I will explain the meanings of these 4. And number 4, experiment is repeated a fixed number of times. Say n times. probability of success remains fixed. Say you denote it by P, small p. If there is an experiment that fulfills these 4 properties, that experiment is called a binomial experiment. And from that binomial experiment, if you define X as number of successes, then this X will follow a binomial distribution. Now I'll give you an example here. The example is, and I'll check all these properties one by one. The example is you have a box of 10 objects. 7 of them are working. 3 of them are defective. You pick 4 with replacement. And you define X as the number of whatever, let's say number of, you define it as working objects. Now, in this whole experiment, this is the experiment and the definition of random variable. The experiment is you have a box of 10 items, 4 are working, 3 are defective, you pick 4 with replacement. That is the experiment. In this experiment, when you pick 4 objects one by one, when you pick the first object, do you have only 2 possible outcomes? Your interest and opposite of your interest, do you have just 2 possible outcomes? Yes, we have just 2 possible outcomes. We have either working or not working. Number 1, picking an object, we have only 2 possible outcomes. That is working, which is denoted by success, and the opposite, not working, which is failure. The second part, this is important now. The second property is that probability of success should be fixed. Now, you called working object as success. Who can tell me what is the probability of success? What is the probability that if you pick one item from here, it will be working? One item, just a one item. You have 10 items in the box, 7 are working, 3 are defective. You pick one of them. What is the probability that it will be working, Faris?
7/10.
7/10. Now, when I pick the first object, the probability that it will be working is 7/10. Is this true for the second object also? When I pick the second object, still the probability of having it a working, is it still 7/10? Jafar?
Yes.
Why?
Because it is with the replacement.
Because it is with replacement and you are putting it back, the size of population becomes 10 again. The number of working becomes 7 again. When I pick the third one, is it 7/10 also?
Yes.
Yes. So each time when I perform the experiment, my probability of success remains 7/10. Number 3, the trials are independent. You pick the first object and then you replace it back. Then you pick the second object. Now, the result of this second trial, that is you pick the second object, the result of the second trial, does it depend upon the result of first trial? Muhammad Faris.
No, it does not depend.
It does not depend. It doesn't depend. The first one was working or defective. Still, the result of the second one, it has nothing to do with the first trial. So the trials are independent. And number 4, Jafar Muhammad.
Doctor, I have noticed that always the question that has with replacement, it is independent.
I will give you the examples. Yes, I will give you some examples. With replacement is yes, special case of with of binomial. Number 4. Before starting the experiment, how many times do you have to do this experiment? The experiment is that you have 10 objects, you have to pick one and you have to check is it working or defective. How many times do you have to do this experiment?
10 times.
4 times. Do you know it before performing the experiment? We know it. Even before performing the experiment, we know we have to perform it 4 times. So the experiment is repeated 4 times. We will not have a 5th trial, 4 times. So this experiment is called a binomial experiment. And from this experiment, if you define X as the number of, what did I define? Number of working, then this X has a binomial distribution. And in the next class, I will tell you what will be the probability mass function of X, what will be the mean of X, what will be the standard deviation of X. I will give you all the shortcut expressions. The most important is to recognize if X is binomial. Yasir Abdo.
Yes, Doctor, should we have the whole probabilities, the 4 probabilities, the 4 probabilities, so we can say it is binomial?
What do you mean by 4 probabilities?
I mean 4 probabilities. Probability 1, 2, and 3. Oh.
If can I pick 10 objects out of 10 with replacement?
I think it cannot.
Can I pick 10? I pick 1, put it back, pick one, again, put it back, pick again, put it back.
Yes.
Yes. Can I pick 20?
No.
I can. I'm putting it back. The size is 10
okay.
again.
Yes. With the replacement action.
I can pick 100. Each time the probability of success will be 7/10. Because I'm putting the object back. Because it is with replacement.
Yes.
Is this your question?
No. I mean, for example, if we succeed in probability number 1 and 2, and we cannot find 3 and 4, is this a binomial trial?
No. If 3 and 4 is not satisfied, it will not be a binomial experiment.
So we should satisfy the whole probability, the 4.
All 4 of them. All 4 of them should satisfy.
Okay, thank you.
Muhammad Faris.
Yes, Doctor. I don't understand the 4th point.
4th point is before starting the experiment, you should know how many times you have to pick.
Just only that?
Yes.
Okay. If I pick 2 means I put 2.
Yes. If you know you have to pick 2, then it's fixed. You know it.
Okay, thank you.
Ali Abdul Rauf.
Yes, Doctor. So binomial is always with replacement.
Binomial is always with replacement, but with replacement is not always binomial.
Thank you.
I think I confused you further. Omar Adnan.
Why should I know how many times I will pick for step or for point number 4?
Because sometimes the experiment is like you have to keep picking until you get 3 working items. So in that case, we don't know how many times we have to perform the experiment. If I ask you that the experiment is you have to pick objects from here and you have to keep picking until you have 3 working. So here you may get first 3 directly working. You may get it on 4th trial. You may get it on 10th trial. You may get it on 100th trial. So in that case, X will not be binomial.
Thank you.
Okay, if you don't have a question at this point, you can leave the session. If you have a question, please go ahead. And after 2 or 3 minutes, I will switch to the office hours team.